Hello students, in this video let us learn about metal-metal junction. In the coming classes we will be studying about junction properties. So we will look into how the junctions behave when we form metal-metal junctions, a metal semiconductor junction and a semiconductor junction. So in this video, we will be discussing about metal-metal junctions. So as we know, a metal-metal junction is formed when two metals are merged together and these metals have different work functions. So as indicated in this figure, work function is the energy required to excite electrons from the Fermi level up to a vacuum level. Vacuum level is the absolute free state. So the energy required to excite electrons up to the vacuum level is denoted by work function of a metal. Suppose two metals have two different work functions, then automatically their Fermi levels will be at different levels. So what will happen when we merge together two different types of metals? Suppose we have two metals. Here obviously the work function of the second metal is greater than the work function of the first metal. Now, when we form a junction, one of the thumb rule for junction formation is that the Fermi level should be continuous across the junction. So, suppose if this is the junction, so before forming a junction, the Fermi level of the first material and the Fermi level of the second material will be at different levels. But right after the formation of junction, the Fermi level should match. Then only that is considered as a junction. So in this case, when these two metals with different work function joins together, they will try to equalize their Fermi levels. And how could they do that? The electrons from the metal 1 will flow into the second metal. So in that way, the Fermi level will be brought into the same level. So as you see here, initially before formation of junction, this is the case. Fermi level of the first metal is higher than the Fermi level of the second metal. And after the formation of junction, the Fermi level equalizes into the same level. That is by flowing of electrons from the first metal into the second one. As a result, the second metal will be charged as negative when compared to the first metal because it has acquired more number of electrons. But since the metals are conducting, this charge will be seen only near the surface, only near the junction, and into the metal there will not be any charge accumulation. Similarly, the metal 1 will turn positive with respect to metal 2. This is called electric double layer in a metal-metal junction. So here we have two layers of opposing charges when two different metals joins together. Near the junction, we will have an electric double layer of positive and negative charge. Now at equilibrium, a contact potential will be developed across the junction, which is given by EV equal to phi2 minus phi1. So that will be the potential, contact potential that will be developed across this electric double layer. And this double layer is confined to the junction regions only. Since a metal is a good conductor of electricity, these charges cannot accumulate into the metal, that will pass right through the metal. And at the junction region, we will have this electric double layer. Now two important effects that correspond to this metal-metal junctions are Peltier effect and Seebeck effect. So in these effects, in these processes, in these phenomena, we are taking advantage of this electric double layer and we will see some effects in a metal-metal junction. For example, in the Peltier effect, you know normally when current is passed through a metal, heat is generated according to the Joule's law. It is given by Q equal to I square RT. If I is the current, R is the resistance of the metal, then Q amount of heat will be dissipated by this metal. But if it is a metal-metal junction, an additional heat is generated, and that heat is usually proportional to current. Here Joule's heat is proportional to I square, but the heat due to the Peltier effect, which is formed in a metal-metal junction, is proportional to current, and the coefficient is called Peltier coefficient, which is pi12 in this case. So when current flows from metal 1 to 2, in addition to the Joule's heat, another heat is being generated, and that phenomenon is called Peltier effect. So when current flows from metal 1 to 2, that is the normal process, from a metal having lower work function to a metal having higher work function, heat will be generated. So current flowing from 1 to 2 will generate heat. And when current flows from metal 2 to metal 1, heat will be absorbed. So this is a very good way to function an electronic refrigerator. So here we do not use any thermodynamic systems. We simply use an electrical setup to absorb or generate heat. So Peltier effect is made use in electronic refrigerator. Similarly, the second kind of effect that we observe in a metal-metal junction is the Seebeck effect. In Seebeck effect, we place these metals, metal 1 and 2, at two different temperatures, T1 and T2. So as a result, the electrons from higher temperature region will flow into the colder side, and this produces a thermoelectric EMF at the junction. So simply by keeping the two ends at two temperatures, you can create an EMF at the metal-metal junction. So this is not a usually observed phenomenon in normal metals. Only in metal-metal junctions you can create an EMF by applying a temperature difference. So this process is called Seebeck effect. The production of a thermoelectric EMF at the metal-metal junction when a temperature difference is applied to the two metals. And thermocouples is usually consists of metal-metal junctions, and they are used widely for temperature measurements. So the Seebeck effect is the basic principle of thermocouples. So I hope this basic properties of metal-metal junction is clear for you. Similarly, we will also try to understand about metal semiconductor junction and semiconductor junctions in the coming classes. I hope today's portion is clear for you. Thank you.